Vint, I would like, part of this series is designed to allow people like you to kind of tell those early stories. So, and this will be a test of your memory to some extent, I guess. But I'd love to know, like, if we can kind of go back to the must be 60s and 70s, what was kind of your world view then? And did you know that when you started working on, these kind of packet networks, which I think is what you did in those kind of early days, did you know you were building something that was going to be huge and world changing, or did you work was it quite insular and you didn't kind of see outside the bounds of those projects?
So, I mean, the honest answer is that, of course, we didn't know at the very beginning how big this would become. On the other hand, while we were working on it, we had a global perspective and we had scaling in mind. But the motivations for this were not everyone in the world is going to have access to this. Because to go back to the history a little bit, the original problem that I was involved in working on, I wasn't in charge of anything, I was just a graduate student at the time, was figuring out how to interconnect a collection of diverse computers from different manufacturers on a packet switch network that would allow them to interwork with each other. And the motivation was provided by the American Defense Advanced Research Projects Agency in 1968, when they issued what was called a request for quotations for the construction of a packet-switched computer communication network. At the time, I was a graduate student at UCLA. I was working on a dissertation that had nothing to do with networking. And this contract was finally let to a company called Bolt, Beranek, and Newman in Cambridge, Massachusetts. And they proposed to build a packet switch network using dedicated communication computers. Were Honeywell DDP 516s, not that that matters to you too much, but they were standardized machines and they weren't very expensive relative to other computers of the day. I mean, there were millions of dollars, large-scale supercomputers, time-sharing machines. These were only $100,000. And of course, in today's dollars, that doesn't seem like much at all. Back around 1968, it was still a significant amount of money, but it was modest compared to everything else. So these specialized machines were called interface message processors. And the reason I go into all this detail, it is important for you and your listeners to understand the context in which all of this is arising. It turned out that the Defense Department, specifically DARPA, had been funding artificial intelligence research from the early 1960s. Now, the artificial intelligence of that day is quite different from what we think of as AI today. It was based on what was called heuristic programming. Make it very simple. Heuristic programs didn't always work. If it always worked, it was engineering. If it didn't always work, it was AI. And so the heuristic programs used clever ideas and notions and concepts to try to get a system to do something better than a person might do. So as an example, at the very beginning, you might want a system that just plays computer games as well as people do. And in these early days, tic-tac-toe was sort of the scope of what a computer program could do, which is not much. Over time, DARPA concluded that the concept was exciting enough that it was worth investing in research. So they had been funding something on the order of a dozen universities to pursue this in the early 1960s. And every year, each of those departments that were doing work in this area kept saying, you need to buy us another world-class computer every year in order to keep us doing world-class research. And even ARPA couldn't afford to buy a dozen machines for everyone. So they said, we're going to build a network and we want you to share your resources, share your results, help us accelerate the pace at which AI research is moving. They didn't really like that, but when they said, we're funding all of you so you don't need to hide your information, share your resources, your computers and everything else. So they agreed to that. And then they said, well, now we have to go build this thing. So I was part of the team at UCLA that was responsible for measuring the performance of the resulting network. And the reason that was important is that Len Kleinrock, the lead of the department or the lab I was working in, had done his dissertation on a queuing theoretic model of the way these store and forward networks would function. And so we were going to make measurements to compare with the predicted results that his students were producing using these mathematical models. And he was the perfect guy to do it. His dissertation was on that topic at MIT, and he came to UCLA in the early 1960s and eventually became one of my thesis advisors. So the whole motivation here was to save money and to share resources and accelerate AI. By the late 1960s, the first packet switches, these interface message processors, were delivered to 4 universities, UCLA, UC Santa Barbara, SRI International near Stanford University, and the University of Utah. And so those 4 nodes were the first 4 nodes of the ARPANET, the Advanced Research Projects Agency network. And so I'm deep into not the design of the interface message processors, but in the host level software. How do the computers use this underlying network to communicate successfully? You need to keep in mind that these machines were made by different companies, Digital Equipment Corporation, Hewlett Packard, IBM, and they were not designed to interwork with each other. I mean, they were really different. Some of them had different encoding schemes for characters. You know, one was ASCII and the other was episodic. Not that that matters to you or the rest of your audience, but they were different, and we had to bridge those gaps. So the host level software that used the underlying packet switch network had to be crafted to deal with all these variations, different operating systems, all kinds of things. So that was what we were focused on while I was a graduate student at UCLA. And it was exciting, was that if we could get it to work, computers of different brands and different locations could communicate across the country. The users who were doing research could use each other's resources. So the early applications of this predecessor PacketNet were remote access to time-sharing systems, you know, just terminal keyboard kinds of things, file transfers back and forth, and very early on, by 1971, electronic mail. That turned out to be the big kahuna when it came to applications of use, because it allowed us to coordinate with each other without necessarily having to be up and awake at the same time. So this computer-mediated communication turned out to be an enormous driver in the early days of packet switch networks, and it worked. So the context in which the internet development happened is with all of that in the background. There was a public demonstration of the ARPANET and some 20 or 30 applications in October of 1972 here in Washington, D.C., near where I am now in Northern Virginia. And it showed a bunch of different applications over by that time, nationwide packet switch network. There were many skeptics who thought this would never work. And one of them was a company very big at the time, AT&T. They had even been invited by the Defense Department to participate in the development of the PacketNet. They said it would never work and they weren't interested, but they'd be happy to sell us dedicated circuits to build our stupid network. So they did, and we did, and it worked. So 1972, late 72, is a big milestone in the story of packet switch communication.
So I'm interested in why AT&T didn't think it would work. Did their engineers just look at it and think this is impossible?
The telephone gets invented in 1876. Circuit switching is the technology that makes the telephone system work, and it makes perfectly good sense. Phone goes off hook, you dial a number, somebody, a human operator and later an automated system makes a connection to the destination telephone, somebody picks up the phone. There's an electrical connection between the two, and it's dedicated to the conversation until somebody hangs up. So it's guaranteed bandwidth, and it's even if no one's talking, the circuit is still there. So perfectly good idea for the kind of application we're talking about. People dial up, it takes a little while to get connected, then they talk for a while, and then they hang up. So the telecommunications engineers of the day had grown up in the circuit switching environment. Problem with computers is that they tend to connect to another computer, blast some data at them, and then shut up and go and talk to somebody else, especially given that these were time-shared machines. So they were running different programs for different purposes, needing to talk to different computers, on a kind of a round-robin basis. And so they would be flinging data out, just like little electronic postcards. And you didn't want to set up a circuit, go to all the trouble of dedicating the capacity, send a postcard or two, and then shut it down again. It's very inefficient, very time consuming. What if you could take the electronic postcard from the host computer, hand it to a specialized packet switch machine that says, he looks at it, says, where is this going? Sends it on its way and says, give me another one. So there's no circuit setup and circuit teardown because the packet switches are all connected to each other in a dedicated way. So you're time sharing the bandwidth that's connecting the various packet switches to each other. It's a very efficient way of doing computer communication. And the ARPANET proved that by showing applications that work very well, including interactive ones and electronic mail and file transfers.
And to go back to where you left off, can you draw a direct line then from that point, 1972, to TCP and IP?
Absolutely. And it involves two things that happened nearly concurrently. I finished my PhD at UCLA in March of 72. This demonstration of the ARPANET is in October of 72. The guy that organizes that demonstration is a man named Robert Kahn, which I did the initial internet design. He was at a company called Bolt, Beranek and Newman that built the packet switches. The head of the project at ARPA was a guy named Larry Roberts. And he asked Bob, please organize a public demonstration of the ARPANET at the International Conference on Computer Communications, which happens to have taken place in October 72 at the Washington Hilton Hotel. So we set up one of the packet switches in the basement of the hotel, and we put up a bunch of terminals, and we organized a demonstration of 20 or 30 applications for anyone who's interested to come and watch and try things out. And just to name drop, a very famous inventor, Robert Metcalfe, who invented the Ethernet in 1973, was the guy responsible for organizing the documentation for the visitors to use to try out these various internet applications through the terminals that were in the display. So October 72 is sort of public announcement of the ARPANET, or visibility of the ARPANET. Shortly thereafter, Bob Kahn leaves Bolt, Beranek and Newman and joins DARPA. And I leave UCLA and become a faculty member at Stanford University, where I had done my undergraduate work. So I'm there with two hats on, or two half hats, a half a hat in the computer science department and a half a hat in the electrical engineering department. And of course, by this time, I'm very interested in computer networking because of the success of the ARPANET. So as I'm going into this early phase of faculty engagement, Bob Kahn shows up at my laboratory at Stanford in the spring of 1973, and he announces, "We have a problem." My reaction was, what do you mean, we? We did the ARPANET, and the ARPANET's working really well. I said, yes. And he said, we're looking now at the possibility of using computers in command and control. Now, it's important to think about this. It's 1973. We use those smaller machines to make the packet switches, and machines are getting smaller and smaller, and it's becoming apparent that machines are going to get small enough that you could put them in mobile vehicles and ships at sea and in airplanes. So imagine for just a moment that maybe using computers to help you with command and control, to deal with allocation of resources and real-time decisions about where they need to be allocated depending on circumstances, was very attractive to the Defense Department. But Bob recognizes immediately that the ARPANET design doesn't work in an airplane or a ship or a mobile vehicle, because we were using dedicated telephone circuits to connect the packet switches to each other. Well, if you use wires to connect the airplanes, they can't get off the tarmac. The tanks run over the wires and they break, and the ships get all tangled up in the wires. So Bob was already working on a mobile packet radio system for ground mobile communication, and also a packet satellite system for long distance communication from ship to ship and ship to shore. His problem, he's got ARPANET, the packet radio net, and the packet satellite net, and they're all different. They're all packet switched. They have different size packets. They have different data rates. They have different latencies. They have different protocols. They have different addressing structures. And every network thought it was the only network in the universe. It had no idea that there was any other network. And he's saying, how do we hook all these networks together and make it look uniform so a computer on any one of the networks could say, I want to talk to the computer on some other network. And the network that they're directly connected to doesn't know that there's another network. So we have to figure out, what should the host computer know in order to say, I want to talk to some other computer on some other network. And if we're not allowed to change the networks, which was a rule, we could not change the networks to know they were part of a bigger collection of networks. So we had to stick something in between the networks that already existed in order to interconnect them without their knowledge. And so we put a little computer in between the networks called a gateway. Today, you'd call it a router. And so its job was to be a host on both of the networks it was connected to. And as far as each of those networks was concerned, it was just another computer on their network. Unknown to them, they were prepared to receive internet packets from a host which did know it was on the internet. The internet packets would get enclosed in a little envelope that would be carried in the packet switched network it was connected to. But when it got to the gateway would rip open the underlying packet, pull out the internet packet and say, where is this supposed to go? Fabricate another envelope to go in the next network and send it on its way. And so the networks didn't know they were part of the internet, but the gateways knew, and of course the host knew. So that design literally emerges out of the rules that we had to follow as to changing any of the networks. So it took took us about 6 months to figure this out, from about March of 73 to September of 73. In the meantime, there's this international network working group, which I was chairing at the time, which is talking about packet switching, talking about interconnecting networks, and exploring a bunch of different ideas. And among them, Bob and I contributed our bit. And eventually we wrote a paper describing how this could work, describing the TCP protocol, which incorporated internet packets and internet addressing as all part of one protocol that would be sitting in the host computers. So we published that paper in the IEEE Transactions on Communications in May of 1974. Now, of course, the publication is sometime months after we'd already prepared the paper. So by January of 1974, before the paper even gets published, I have a team at Stanford working on the detailed specifications of TCP. Now, that takes us a whole year. And in December, we publish a detailed spec for how this could work. And to fast forward just a little bit, we start implementing it in January of 75. 3 different groups are working on this: Bolt, Beranek, and Newman, the original ARPANET builder; University College London in London, because it's actually on the ARPANET and eventually on the packet satellite net; and Stanford University, where the work originally started. So the 3 groups are building implementations of the TCP protocol. We start using it and it doesn't work exactly the way we expected. So we went through 4 iterations, design and implementation, based on our operational experience. And in the middle of all that, we realized that the TCP, which is working really, really hard to make sure everything gets to the destination in the right order, duplicates are filtered out, disorderly arrivals are straightened out. All of that's working really hard for reliability. And then we realized for certain kinds of applications, getting all the bits there is less important than getting them there as quickly as possible. So for voice communication and for video and for radar tracking, it's okay if you lose some data, not a lot, but some. So if this were a video call, a lost packet would be a blip in the video frame and it's gone. And if I didn't hear what you said, I'd say that again. For radar tracking, you don't want to know where the missile was. You want to know where it is now. So you don't mind if you lose some radar data, as long as you get the latest stuff as quickly as possible. So we split the internet protocol out from the TCP and made the TCP the end-to-end reliability mechanism. And the IP layer now supports just packet delivery without repetition and retransmission or error correction or anything else. And then we glue a kind of user datagram protocol interface on IP for the real-time traffic. So by the time we get done, it's like sort of mid-1978. We've now standardized or stabilized the TCP IP protocols, and now we're ready to start implementing it on every operating system we can get our hands on.
And that paper you published with Bob Kahn, is that the one where I think the first use of the word internet?
No, it wasn't actually. It never used the word internet in the 1974 period. We called it internetworking.
Okay.
To be honest with you, that got very tiring to say, internetworking. In December of 1974, we published a request for comments. It's a standards document from the Internet Engineering Task Force. And the label said the specification of the Internet Transmission Control Protocol. And so that was the first written use of the word internet in December of 1974.
Okay. And was it at this point then, once kind of the IP, the Internet Protocol was established, did you have a sense now that this could become something pretty big and global and useful for everybody, or was it still quite...
Well, no. To give you a very clear example, at first I thought this was an experiment. I mean, we could not necessarily have an idea that this is all going to work well. So as it happens, I'm at Stanford from 1972, late 72, until 1976. And during that time, we're going through these iterations of the protocol, and I'm more or less leading the Internet TCP IP effort. And of course, I'm getting a huge amount of help from graduate students at Stanford and others at BB&N at University College London. However, around 1976, sort of March or so, I get a call from ARPA and they say, listen, why don't you just come back and run the whole program? And that meant the internet program, the packet radio program, the packet satellite program, the packet security programs. We're looking at packet cryptography in order to protect end-to-end communication. On the scaling question, when we first started this work, Bob and I are talking about, well, so, how many addresses are we going to need for this thing? And we thought, well, we just finished building the ARPANET, and that was a fairly big deal. It was a nationwide, eventually international thing. We figured there weren't going to be too many of these big networks. And we thought, well, maybe there'll be 2 per country because, you'd want some competition. We also wanted very much for this technology to be made available to our allies, because if this is going to be the basis for the American command and control system, it has has to interwork with the command and control systems of our allies. So they need to know about this technology in order to be compatible. This is what led us to decide not to patent it, not to provide any barriers for access, to publish the designs, the protocols, and even the reference implementations openly without any constraint, because we wanted it to be available to all of our allies. We'd also gone through another little exercise. We said in 1973, so who are our allies? And we had this list. Then we said, who were our allies 25 years before? And it was a different list. And then we said, who will our allies be 25 years from now? We didn't know. The only way to make sure our allies get access to this is to publish it openly. Of course, that means that our adversaries will get access too, but our intent was that it be widely available for everybody. And that would make sure that our command and control system could made to interwork with all the others that needed to, because they'd all be using the same set of protocols. So that's what drove us to make this so broadly available without any constraint.
And was that, I'm fascinated, having been to a few of the kind of the regional internet registry meetings myself now. I mean, when you talk about your colleagues, your peers, it sounds like one big team all pushing in the same direction together and everything being very hunky-dory and everyone agreeing on how this should move. But I'm sure, having seen the internet community kind of work, there must have been disagreements and arguments about certain things.
There were lots.
Yes. What were the kinds of things that kind of weren't agreed upon between you and your peers? And
let me go back to the scaling question, though, because when Bob and I were trying to figure out how much address space was needed for the internet research project, we calculated that, we said, how many countries are there? And we guessed at 128. That was wrong. There was actually more like 170 or something back then. But we guessed 128 because there wasn't any Google to go to ask the question. And we didn't think to pick up the phone and call the United Nations. And besides, 128 is a power of 2, and that's what engineers think in. And then we thought 2 per country, so that's 256. That takes 8 bits of information to represent 256 possible networks. So in this address field, 8 bits is given over to which network is the internet packet going to. Then we said, well, how many computers will they be per network? And we thought, well, why don't we be generous and 24 bits? That's 16 million computers. This is 1973. Computers are hundreds of thousands of dollars each. And so 16 million is a lot per network. So we allocated 32 bits for addresses on the internet. That would give us enough address space, if it were used very efficiently, to label on the order of 3.4 billion terminations. And I thought, while I was running the program, that's got to be enough to do this experiment. We're never likely to, that's more than there were people in the world at the time. So that's where the 32-bit address came from, and it's sometimes referred to as IP, Internet Protocol version 4.
Yeah.
Around 1992, we realized that we're going to run out of address space, and the reason for that is an invention that happened in May of 1973. Except I certainly didn't appreciate the implications of that experiment, that invention, and that's the Ethernet. So Bob Metcalf, the guy who did the scenarios for the ARPANET demonstration in October 72, is the inventor, along with David Boggs, of the Ethernet, which allows you to create a local area network very efficiently and at very high speeds. Even his first version was up in the 1.3 or 1.4 megabits per second data rate. I did not fully take on board the implications of low-cost local area networking. But by the 82 or so, Bob leaves the Xerox Palo Alto Research Center and starts a company called 3Com to make Ethernet interfaces that you can use to connect computers to each other. And so between that technology and the fact that other agencies of the US government were starting to invest in backbone internet-based networks, the National Science Foundation starts to build the NSFNet backbone in 1985 or so. NASA starts building a backbone network called the NASA Science Internet. The Department of Energy starts building the Energy Sciences Network, ESNet, and of course there's the original ARPANET. So there are 4 big backbone networks that are emerging in the mid-1980s, supported by the US government, plus a rapid proliferation of local area networking to bring universities onto the internet because it gives them access to supercomputer resources the Department of Energy and NSF were using. So Bob and I were worried about scale, and we clearly missed the mark because of the rapid consumption of address space thanks to the local area networks. So a new version of the protocol was developed in 1992 and finalized in 1996 called IP version 6. It had 128 bits of address space, which is 3.4 times 10 to the 38 addresses. And I just realized I made an error in my computation. 2 to the 32nd is actually 4.3 billion, not 3.4.
Right. Mm-hmm.
3.4 times 10 to the 38th addresses in IPv6, and 4.3 times 10 to the 9th addresses in the 32-bit address space.
Mm-hmm.
It was indeed more than there were people in the world at the time.
I mean, I thought you were going to say the invention that changed things was the invention of the personal computer or something like that, which just kind of allowed everybody to kind of come on board as well. But the Ethernet was even more influential.
Yeah, the Ethernet allowed terminals that were properly configured to get access to time-shared machines.
Right.
Workstations came along in the mid-1980s, Sun Microsystems being an example of that. And the other thing which really helped to trigger all this, in addition to the local area networking, is the introduction of the Unix operating system by AT&T of all places. AT&T makes it relatively easy to get access to the source code. Berkeley, University of California, Berkeley, released a version called Berkeley's Unix. It was called BSD, was the release, and BSD 4.2, which is somewhere in the mid-1980s, has TCP/IP built into it. And since it's so widely available, universities all over the place are acquiring access to Unix, putting it onto workstations, buying Ethernet capability, and building local networks on campuses to be interconnected to the National Science Foundation network or to its intermediate level networks. So NSF says, let's build a core network, and then let's build a bunch of intermediate level networks to handle the thousands of universities in the United States. So they had a dozen of those intermediate level networks. So there's this configuration of different networks all being interconnected, which is what the internet was designed to do.
Mm.
And so people took advantage of its intent, which was to allow multiple networks to interconnect and hosts on those networks to interwork, to design and build a bunch of different networks all coalescing in what we call the internet today.
Mm-hmm. And was that the moment then when you thought, oh, this thing is going to be really big, international, global?
No, even there, it was still a purely academic thing, except the Defense Department was using it, of course, with its own system starting around 1983, which is when we turned the internet on operationally. Roughly on that day, we called it a flag day, we separated the research internet from the military network, MilNet. So all the military guys moved over to one network, and they're interconnected by gateways to the continuing research internet. But the thing that caused me to realize that this was going to be a big deal doesn't come until 1988. Now you have to go back and into 1986 to see what happens. One of my colleagues, a man named Dan Lynch, who had worked on the internet, had worked at SRI International, one of the second node on the ARPANET, and then at University of Southern California Information Sciences Institute. He ran the data centers there. They were very engaged in running experimental versions of the TCP/IP protocols while the older ARPANET protocols were serving all of the users. He decides around 1986 or so that this is a big deal, and he starts a company called Interop, which stood for interoperability. It starts out first as a training ground to show people how to design and build pieces of internet, designing and building TCP/IP and all the operational stuff that goes with it. Very, very quickly after starting out as a training operation, he turns it into a trade show because he brings this giant fat Ethernet yellow cable to the show, and he tells all of his participants, if you want to show your stuff at my show, you need to show it interworks with everybody else. So plug yourself into this giant Ethernet backbone and demonstrate that you can work with everybody else. Of course, this was a huge challenge, and a couple of days before the show opens, everybody is debugging everything left and right because they're finding places where things don't work. It was a fantastic incentive to get bugs out of the system. And so when people walked into that show, they were seeing dozens of different companies with dozens of different applications and hardware and software running interoperably on a high-speed Ethernet. So this really triggers everything. In 86, a couple hundred people show up just to, how does this work? 1988, 50,000 people show up at Moscone Center in San Francisco to kick the tires, to see how this stuff works. So I walk into the show with the then CEO of 3Com, the company that Bob Metcalf started, Eric Benamou. And the first thing I see is a Cisco 3-story level display. It's so big that it's got room for people to go up the stairs, and they've got equipment on all 3 floors. They're doing demonstrations. And I just stopped, with my jaw on the floor. And I turned to Eric and I said, how much does that cost? And he said, a quarter of a million. This is 1988 when a quarter of a million was a significant amount of money. And then he says, and that doesn't include, the cost of the people for a week to make booths. And I just stood there and I'm thinking, holy crap, somebody thinks they're going to make money out of the internet. And immediately I'm starting to think, well, how in the hell is the general public and the private sector going to get access to this thing? Because up until that point in the US, it was all government sponsored. So the whole market for Cisco at the time was the research community and universities that are starting to use networking as part of their normal day-to-day operation. So now I'm trying to scratch my head saying, how do I get the general public up on the system? And I run smack into a restriction on the NSF net and all of the networks is that no commercial traffic is allowed to flow on the government-sponsored backbones. So, so much for getting the general public and the private sector. So then I'm thinking, well, let's see. I had built a product for MCI, an international telecom company, called MCI Mail, which was a commercial email service. And I did that in 1983. And so it's 1988. And I'm thinking, well, why don't I propose to the Federal Networking Council, which is the organization that made policy about internet access, why don't I propose to interconnect the commercial MCI mail system to the internet, specifically the NSFNet backbone, just to see if it could be made to work? Well, of course, I knew it could be made to work because I designed both of them. But they said yes. So in the summer of 1989, we put up an email gateway connecting the MCI mail commercial system to the internet. And suddenly everybody on the internet has access to all of the subscribers to the MCI mail system. As soon as we announced this, all the other commercial email providers, Telenet, Telemail, and Geisco, and a number of others, say, well, wait a minute, those guys shouldn't have privileged position. We want to be on the internet too. And the Federal Networking Council agreed to let them do that. And so two things happened in 1989. First of all of these isolated email systems that could only talk to their own subscribers could suddenly talk to everybody on the internet and each other. And I think that kind of shocked them all when they realized that because they were adopting the same standards to work with the internet, it meant that they could interwork with each other. So suddenly all of their customers could talk to everybody else's customers. And then the second thing that happens in 1989 is that 3 commercial internet services pop up. One of them is called UUNet, one of them is called PSINet in Northern Virginia, and the third one was called SurfNet, spelled CERFnet, in San Diego. So suddenly we got 3 commercial internet services in 1989. So during this 1989 period, now I'm getting the message. This is going to be a big deal.
Presumably that was all still very big in the US. Did you realize it was going to be international as well?
Well, by that time, we already had seen significant implementation in Europe, especially in Northern Europe. The Scandinavian countries were very advanced in their thinking. Okay. But we had collaborations in Germany and Italy, the UK and Norway along the way. And so there was already some international interest in this, but it skyrocketed in the mid to late 1980s. So now what I haven't said anything about, and you had asked much earlier and I didn't answer very well, what about the tensions and tussles? There was a notable tussle over which of several possible options for internetworking were going to become the standard. So in the mid-1970s, Larry Roberts, a name that I mentioned a long time ago, who helped to lead the ARPANET development, joined both Beranek and Newman to found a company called Telenet and to invent a new protocol called X25 and X75, which is for network interconnection, for what was then called the Consultative Committee on International Telegraphy and Telephony, CCITT. Today it's ITUT. So Larry and colleagues in Canada, France, and the UK developed the X25, X75 protocols and standardized them in the mid to late 1970s. So that is one potential internet system, international networking system. Then there is the TCP/IP work. And then in 1978, a number of European colleagues, some of whom had participated in the International Network Working Group, decided that they didn't want to have anything to do with this US Defense Department thing and decided to go design and build their own architecture called Open Systems Interconnection. So we have OSI, we have TCP/IP, and we have X25, X75, all potentially vying to be the international standard for internetworking. And over a period of time, internet slowly emerged as the winning choice until roughly about 1984 or so, it's pretty clear that that's the preferred option for most networking. But it was not a slam dunk at all. There were lots of fights. There were governments that said we should standardize on the Open Systems Interconnection model because it's coming out of the International Standards Organization, not out of this funny IETF and this Defense Department thing. But what I think contributed to TCP/IP's adoption is the fact that we'd implemented it broadly on many different operating systems, most especially Unix. There were local area networks that you could buy off the shelf to expand the system. And there were routers that you could buy to build wide area networks, both originally Proteon and Cisco systems, and eventually Juniper, and of course Huawei and many others now. The commercialization, I think, is what gave the edge to the TCP/IP protocol suite.
Right, got it. And I guess at this point then, or I'm not sure if it's around this time or a little bit later, but when this thing starts to grow and it becomes commercial and international, organizations start to form up around it. You know, you've mentioned IETF, there's ICANN, of course, that you were on as well. You were on numerous organizations and chaired many. That political side of the internet, how did you see that growing? And what was your kind of influence and input on those kinds of political and corporate governance, if you like, dimensions?
Well, Bob and I both were excited about trying to make this as open as possible. We said, listen, if you can figure out how to build a piece of the internet, go find somebody to connect to. And if you use the same protocols, it should work. We didn't dictate what the business models were. Some were free, some were government sponsored, some were for profit. We didn't dictate who you should connect to. We just said, find somebody and work out some arrangement on agreeable terms to get interconnected so that the thing could grow organically. Then most of the time that tended to work. As the system grew, we needed to create institutions to help deal with the scale. So as an example, early on in this development in 1979, Bob and I have got most of this in our heads. We've got a small number of, a few dozen people who are really focused on this stuff. And Bob, by this time I'm at ARPA, and Bob says, what happens if you get hit by a bus? And I said, well, I hope that wouldn't happen. He said, yeah, but what if it did? He said, who has all the stuff that's in your head? And I said, well, I do. And he said, yeah, well, that's the point. So he said, you got to do something, create a kitchen cabinet so that if anything happens to you, we have the knowledge that we can continue. And I said, okay, we'll set up something. We'll call it the Internet Configuration Control Board. I wanted it to be sounded as boring as possible so nobody would want to be on it. And then I had appointed the people who were leading the research work to be on the ICCB. Eventually that became the Internet Activities Board, which was the Internet Advisory Board, then it became the Internet Activities Board, and then it became the Internet Architecture Board. And so IAB was an institution that got created in the late 1970s at need. It spawned the Internet Engineering Task Force and the Internet Research Task Force as it grew and as those activities needed to have their own structure. Eventually, their focus of attention, of course, was mostly on standards and on speculative protocol design. A person who was handling allocation of IP address space and domain names was John Postel, who was a researcher who had been at UCLA with Steve Cocker and with me during the ARPANET days, and then went on to USC, Information Sciences Institute. He was publishing as the editor for the RFC series, which now numbers in the 9,000 to 10,000 documents. He was handling IP address allocations in a notebook initially, and also domain name allocations. So it's incredible. This one guy with enormously good engineering taste is responsible for all three of those activities. Well, eventually that gets to be too much for one guy or even a small group. So it becomes necessary to create an institution to do that. And the White House was instrumental in pushing that in the 1997, 1998 period. And out of that negotiation and debate came the Internet Corporation for Assigned Names and Numbers, which was given responsibility for IP address allocation and domain name allocation. And so that, again, was an institutionalization at need in order to deal with scale. Similarly, when the domain name system was developed, we needed to have somebody serving the root to everyone who needed that information. And we just John Postel just looked for volunteers and picked something like 13 different organizations, some commercial, some government, some private sector or nonprofit, to run the distribute the root zone to domain name resolvers at need. And so John does that for a while, and we have an informal collection of root servers that just cooperate with each other, one of which, in this case, VeriSign, produces the original root on a twice-a-day basis, which ICANN digitally signs, and then it goes off to be distributed. So institutions keep getting created as they seem to be needed, either for scale or purpose. That's true for the allocation of IP address space. Eventually, John could not do that on his own. He looked for help, and eventually regional internet registries like the Breitband CC in Europe and the
ARIN and APNIC.
America's Registry for Internet Numbers gets created, and APNIC also gets created for Asia Pac. And then a little bit later, the LACNIC in Latin America, Central America, and AFRINIC in Africa. So that becomes codified, some of it before and some of it after the creation of ICANN.
Got it, Vince. There's two more questions I'd like to ask you. One of which would be, when you look back, would you have done anything differently? Do you think, when you describe it, it sounds like it's fairly organic and it comes out of a need and a necessity, and things kind of seem to move quite smoothly.
Yeah.
But what could you have done better, or what could have been done differently to make things, I don't know, happen faster, more economically, more efficiently?
Well, I look back on things that I wish had been an opportunity, but they probably were not at the time. For example, cryptography and its use for protection of traffic. In the early days, in the 76, 77 time period, we didn't have access to public key crypto. The first paper was published in 1976, but it didn't come with an implementation or anything. So, well, there was the Diffie-Hellman key generation thing, but that was about it. I had been working on packet cryptography since the mid-1970s for DARPA and for the National Security Agency. If we had had public key cryptography available to us a little earlier, and it would have been if the Brits had agreed to release it, which they didn't. At GCHQ, they invented the concept in 74. Now, if I had known about that, which I didn't, I would have, I think, understood that would be a great way of doing key distribution, which was otherwise a really hard problem that didn't scale very well with the technology of the day. So that's one thing that if I had had the opportunity, but the public key stuff came just a little late, and I was so eager to get this implemented and running so we could see if it would work at scale.
So has that happened now? I mean, and
yeah, look at what we've got: HTTPS, TLS, Quick. Okay. We're using, digital signatures for blockchain. I mean, the public key crypto has been an enormous enabler. Mm-hmm. In the same sense that the World Wide Web has been a huge enabler, and the mobile phone, the smartphone has been a huge enabler. Every one of these steps has made it possible to do things with this architecture that we couldn't have done before, some of which was not anticipated. Mobile phones were around for a long time. They first showed up in 1983, but the smartphone doesn't show up until 2007, thanks to Steve Jobs and his amazing ability to assemble a different set of technologies that are spectacular in combination. And we're still learning that. And of course, now we're into the AI period where, despite its, sort of frenzied craziness, there's real substance there. And that's transformative once again. And who knows, 10 years from now, it'll be something else.
Well, that's a nice segue to my final question. We spent this whole call looking backwards. Let's look forwards then for a couple of minutes. I know you do I just read about it today, interplanetary internet and all this sort of stuff. Maybe just spend a couple of minutes talking about some of the most exciting things you're currently either working on or seeing other people work on.
Okay, so here's what's clearly coming. First of all, more high-capacity subsea cables running at 800 gigabits per second per channel, which is just mind-boggling, considering the original ARPANET was 50 kilobits a second in the backbone, and that was fast in 1969 and 1970. Second, there is low Earth orbit satellite constellations, Starlink being the oldest of them, but others are coming, providing access literally all around the globe. Now, whether it's affordable or not is an arguable question, but the fact that it theoretically provides coverage to every square inch of the planet is really something. The interplanetary system has been underway since 1998. It involves the NASA, it involves the European Space Agency, the Japanese Space Agency, the Korean Space Agency, and any others that are interested, been standardized. The new protocols, they're not TCP/IP. They are called the Bundle Protocol Suite, and they deal with the fact that the distances between the planets are literally astronomical. We're talking minutes to hours to even days of propagation delay between endpoints in the interplanetary architecture. And there's also disruption. The planets are rotating, you lose contact, or maybe a satellite goes behind the planet, or one of the spacecraft that's on a trajectory that you can't see for a while. So it's a variably delayed and disrupted environment, which is much more difficult to deal with than the TCP/IP protocols have been designed to do. So we've developed a new suite of protocols and standardized them with the Consultative Committee on Space Data Systems and the Internet Engineering Task Force. It's on the International Space Station. It's been tested in space in various distances. We expect to be part of the Artemis return to the moon missions that are happening collaboratively and cooperatively with some 54 different signatories, including ESA, JAXA, and CARI, and the US NASA. So the vision here is essentially the deployment of a potentially optical as well as radio-based interplanetary scale network, solar system-wide internet, which can be deployed step by step as equipment gets out there, maybe finishes its scientific mission and wants to be repurposed as a node of the interplanetary backbone. This real engineering. This is not science fiction. So that's coming. Then there's another project that we don't have time to go deep into, but it's called the Interspecies Internet. And if your listeners go to interspecies.io, you'll learn more about the possibility of using the internet to connect non-human species to each other, and potentially to use artificial intelligence to translate from one species to another, assuming that the signals of species A can be made to be understandable to species B. And you would say, well, what does a whale have to say to a chimpanzee? We have evidence that there are interactions between species as well as within species. We're learning through the Interspecies Internet program to interpret those signals, whether they're visual or audible or a combination. And so the internet could be used using artificial intelligence to do transduction between those. So that's another important project that's underway.
That sounds amazing. We could probably spend another hour speaking just about that. That sounds crazy. I'm going to look that up straight after this. But Vint, thank you so much. That was amazing. That was brilliant. Thank you so much for your insights there.
Well, thank you. It's a real pleasure to have a chance to try to, dump core, as they used to say. There are so many people that didn't get mentioned that deserve mention, which is why Andrea Vea, who wrote How We Created the Internet interviews, is very important to you. So please take advantage of that.
Sure, will do. Thanks for that little nudge there as well. Yeah, cheers. Thank you, Vint.